Module 2.1, Limits. Objective 1, define and determine limits using left and right-hand limits. Objective 2, determine the limits of polynomials. Objective 3, determine limits of square root functions. Objective 4, determine limits of rational functions with restrictions in their domains. Objective 5, determine limits of piecewise functions. Objective 6, determine limits of difference quotient. In Objective 1, we're going to define and determine limits using the left and right-hand limit. The concept of limits. It is important for us to study how the domains, the x values from left to right, interact with their ranges, the y values or heights. Some functions will transition smoothly, while others have breaks or gaps in their ranges. A limit of a function exists only if a range or a height of a function is approached infinitely close from both the right-hand and left-hand side. In this section, we will observe functions that either approach a common height from left and the right, or approach different heights in which the limit does not exist. Let's take a look at our first example where we're going to look at a limit from the right-hand side. In this case, we're looking at the limit of f of x as x approaches 2 from the right-hand side. So we're looking as x approaches 2 from the right-hand side. That means as we're going toward 2, which is the x value, toward 2, or the domain, we are looking at what height this is approaching. And it's coming down, and notice that it comes to 3. So the answer for this one would be 3. All right, let's look at our second example, a limit from the left-hand side, or a left-hand limit. Here we're looking at the limit of f of x as x approaches 2 from the left-hand side. Notice that in this case, as we approach 2 from the left, which is this notation, so we're coming from the negative on the left side, as we're getting closer and closer to this x value 2, our height is going to be equal to 5. And so that would be the answer to this one. Example 1, a limit from the right-hand side. In this notation, we're looking at the limit of f of x as x approaches 2 from the positive side. And that's what that notation states. Notice that in this function, as the x values go closer and closer and closer and closer to 2, that the y values, or the f of x values, are headed closer and closer and closer to what number? And the answer to that would be 4. In the second example, we're looking at a limit from the left-hand side, where we're looking at the limit of f of x as x approaches 2 from the negative side. Here, as we look at our domain, we're looking as this x value is getting closer and closer to 2. What's going to happen with your y values, or your f of x values? Really getting closer and closer to, and the answer to this would be 7. And so the limit of the f of x as x approaches 2 from the left or the negative side would be equal to 7. Concept. To reiterate the definition, we must remember that in order for a limit to exist, the left and right-hand limit must approach the same range, or the same height. Let's observe a few graphs that illustrate this concept. In the first example, we're looking at the limit of f of x as x approaches 5. The limit as x approaches 5 from the left is that notice as this heads toward x equal 5 from the left-hand side, that our height would approach 2. And notice, let's check the limit of f of x as x approaches 5 from the positive side, or the right-hand side. Notice as it approaches 5, or the x equal 5 from the right-hand side, it also equals 2. The height would be equal to. So the limit, since it is both from the left and from the right, the limit would indeed, in this case, equal 5. In example 2, let's take the limit of f of x as x approaches negative 2. Notice that in this case we have a vertical asymptote running at -2. As our function approaches -2 from the left-hand side, this direction, notice that it heads toward positive infinity. Notice as the function heads toward -2 from the right-hand side or the positive side, it also approaches positive infinity. So the limit of f of x as x approaches -2 from both sides would be equal to positive infinity. We're looking at the limit of f of x as x approaches 3. Once again, we have a vertical asymptote, this time at x equals 3. So let's take a look at the limit as x approaches 3 from the negative side of f of x and see what we get. Okay, so if we're approaching 3 from the negative side or from the left-hand side, notice that we're going to get positive infinity. Okay, let's look at the limit as x approaches 3 from the positive side of f of x. And from the positive side as we head toward 3, so we're heading this direction, notice that we're going to get negative infinity. So notice that these two answers are different. Therefore, this limit does not exist because in our definition we stated that they had to be the same. And in example 4, we're looking at the limit of f of x as x approaches -4. Notice that in this function, we have the limit of f of x as x approaches -4 from the negative side. Let's see what we get. So we're coming from the left-hand side, and we're approaching height 3, aren't we? And let's take a look at the limit of f of x as x approaches -4 from the right-hand side. So from the positive side, and we are heading toward 6. Even though it never reaches 6, we're heading toward 6. Once again, these two answers are not the same, so this limit does not exist. Objective 2, determine limits of polynomials. Note that polynomials, that's the functions in this form, where a, b, and c, these are real numbers. A, b, and c are real numbers. And notice that my exponents are descending, so they're going down. And these are smooth throughout their domains. Okay, let's look at example 1, where we're looking at the limit of x minus 3 as x approaches 5. So we're going to be looking as x approaches 5 from both. Now in this function, as we approach 5 from the negative side, we're heading toward height 2. And notice as we approach 5 from the right-hand side or the positive side, we're also arriving at height 2. So, since it works from both sides, we know that the limit as x approaches 5 of x minus 3 is equal to 2. Now, a funny thing here, since polynomials are smooth and we are arriving toward 5, we are able to substitute the 5 in for x, and x minus 3 would be equal to 2. So notice that this is going to be the answer to the limit, and this works for all polynomials. In example 2, once again we have a polynomial, and we are looking at the limit as x approaches 2. Since we know that the polynomial is smooth, we're going to be able to once again substitute the 2 in for the x. That'll give us 2 to the 4th power, which is 16, 2 to the 2nd power, which is 4. And that should give us 23. So notice the limit of this polynomial as x approaches 2, we can solve by using simple substitution. And again, this limit will be equal to 23. In objective 3, we're going to determine the limits of square roots. Note that square root functions have no left-hand limit where the inside of the function is equal to 0. However, everywhere else it is smooth and a limit exists. So what we're going to do is we need to remember that whatever's underneath the square root cannot be negative. So that means that 2x minus 3 must be greater than or equal to 0. So we're going to add 3 to both sides. That'll give us 2x is greater than or equal to 3, and we're going to divide by 2 on both sides. So x must be greater than or equal to 3/2. So this is going to be our domain. If we look at the graph of this function, we notice there is no way that this function can exist below 3/2. But since we're looking as x approaches 5, this is just like the polynomial where it's smooth everywhere above 3/2. So here all we have to do is substitute the 5 in for the 2, and we'll find out what height that this approaches. So if we plug in the 5 in, and we would get the square root of 7. So this height right here would be the square root of 7. So the limit of this square root as x approaches 5 would be equal to the square root of 7. Objective 4. Determine the limits of rational functions with restrictions in their domains. Now we must remember what we learned in section 1.3 about rational functions. Rational functions have holes in their domain when the restriction in the denominator has a common factor in the numerator. If the restriction in the denominator has no common factor in the numerator, then there is a vertical asymptote. Sometimes the asymptote allows the limit to exist because the function is heading toward the same height, and sometimes it heads in different direction, causing the limit not to exist. Let's look at a few examples of these. In our first example, we're looking at a rational function that will have a hole and a vertical asymptote. The first thing I'm going to do with this rational function is I'm going to factor so that I can see if they have a common factor in the numerator and the denominator. Notice that we have two restrictions in our domain. The first one, we know that x cannot be equal to 0. And notice that there is no common x in the numerator. Therefore, this is a vertical asymptote. Notice also that x minus 2 is a factor in the denominator, and it can't be equal to 0. So if we add 2 to both sides, then we get x can't be equal to 2. So this is our second one, but this one does have a common factor in the numerator. Therefore, this one is a hole. So, in this case, let's take a look at this function. Notice that our vertical asymptote runs at 0. Okay, so we have the function split into the left-hand side and the right-hand side. And notice also that in our second restriction of our domain, we had a hole. So at 2, we have a hole. Now we're looking at this limit as x approaches 2. And so what we're going to do is we can cancel these two factors to simplify this function. Cancel the two factors, which will give us 7 over 2. And if we have 7 over x, where x approaches 2, then that is where the hole is going to be. And it's okay for it to have a hole because it's going to approach 7/2 both from the right-hand side and from the left-hand side. Therefore, our limit will be 7 over 2. In this one, we have the restriction in the domain where x minus 3 cannot be equal to 0. So I'm going to add 3 to both sides. And so x cannot be equal to 3. Notice that this restriction in the domain does not have a common factor in the numerator. Therefore, this one is going to be a vertical asymptote. So at x equals 3, we have a vertical asymptote. This function should look like this, and like this. And we are looking at this as x approaches 3. So notice as we're coming toward 3 from the left-hand side, we're heading to negative infinity. From the right-hand side or the positive side, notice that it heads to positive infinity. So notice that it's heading to two different numbers, therefore this limit does not exist. Notice in this function, we're going to have two vertical asymptotes where I factor and get x plus 2 and x minus 2 from the difference of two perfect squares. And so x plus 2 cannot be equal to 0. Subtract 2. So x cannot be equal to negative 2. And the other one is x minus 2 cannot be equal to 0. So I'm going to add 2 to both sides. So x can't be equal to 2. So I have two vertical asymptotes, one at negative 2 and the other one at positive 2. And our function should look something like this. And this. And like this. So because of the two vertical asymptote, this graph's really split into three parts. Okay, now we're going to look, and we need to look as x approaches 2. Well, as it approaches 2 from the negative side, we're heading to negative infinity. And as we're approaching 2 from the positive side, we're heading to positive infinity. So here's another case where this function does not exist because they're heading to two different numbers. Objective 5, determine the limits of piecewise functions. Note, piecewise functions are also great to help illustrate the concept of limits. Because of their ability to stop and start on the domain, they emphasize the existence or the lack of the existence of limits. Let's look at the first example. Here we are dealing with a piecewise function, and let's take a look at this piecewise function on a graph. Notice this graph has three parts. First, it acts like negative x plus 2 everywhere below 2 and equal to 2. So notice that it is 2 inclusive. Notice that between here and here, the second part runs true. Between 2 and 4, it is running in here, and these are open intervals or open dots. And then the last one closes in the end of that and then heads downward. Okay, so let's look at the limit of this piecewise function as x approaches 2. Well, as it approaches 2, the limit of p of x, well, as it approaches 2 from the left-hand side, it's going to be equal to 0. As it approaches 2 from the right-hand side, it's going to equal to 4. Right here. And so this limit's not going to exist because it's heading from two different things. In the second portion, let's look at as x approaches 4 from the left-hand side, we've got it reaching 6, the value 6. As it approaches 4 from the right-hand side, it's going to approach 6 also. So in this case, the answer will be 6 because it approaches both from the left and from the right to the same number. And in the last section, we are dealing with a polynomial. Now notice 6 is well into this polynomial. So as we're heading towards 6, we're going to be able to substitute 6 in to find that height. So it's going to be 22 minus quantity 6 squared, which is going to be 22 minus 36, which should give us negative 14. And so the limit of this one would be equal to negative 14. Objective 6, determine the limits of the difference quotient. In section 1.1, we introduced the difference function. The formula for the difference function was f of x plus h minus f of x over h. Now we're going to introduce applying limits onto our findings in that section. In example 1, we want to find the limit as h approaches 0 of the difference quotient given that f of x is equal to 3x minus 7. Well, if f of x is equal to 3x minus 7, then we're going to substitute x plus h to start off with. So we're going to have 3 times x plus h minus the 7 minus f of x, which is minus 3x minus 7 all over h, which is going to give us 3x plus 3h using distributive property minus the 7, distribute the negative, which will give me minus 3x plus 7 all over h. Notice that the 3x's will cancel, and so will the 7's. So now we're looking at 3h over h, and we're going to take this, we're going to take the limit of this as h approaches 0. Well, notice that we can't substitute 0 in yet because it's a restriction in the domain, but notice that the 3's will cancel. So the limit as h approaches 0 of 3, well, this is going to be a line with height 3 all the way across. So as h approaches 0 from this side and from this side, we're going to be equal to height 3. Example 2, we're going to find the limit as h approaches 0 of the difference function given that f of x is equal to negative x squared plus 9x minus 7. So again, we need to remember that the formula for this is, here we go, all over h, and we're going to do this limit as h approaches 0. So first we do the substitution by plugging the x plus h in, so that'll be minus x plus h quantity squared plus 9 times x plus h minus the 7 minus the function, which would be negative x squared plus 9x minus 7 all over h. And we're going to take the limit as h approaches 0. Okay, now let's do our algebra. So that's going to be minus x squared plus xh plus xh plus h squared plus 9x plus 9h minus the 7 plus x squared minus 9x plus 7 all over h. And we're going to take this as a limit as h approaches 0. Distributive, so that will give me minus x squared. And I'm going to combine these two xh's. That's minus 2xh minus h squared plus the 9x plus 9h minus 7 plus x squared minus the 9x plus the 7 all over h as h approaches 0. Now if we can combine our like terms, we can look here and notice that the x squareds are going to cancel. We're also going to notice that the 9x, the positive and negative 9x's will cancel, and the minus 7 and the positive 7 will cancel. So that's going to leave me with negative 2xh minus h squared plus 9h all over h, and that's the limit as h approaches 0. Now notice that all three of the numerator have an h in them, so I'm going to factor out an h. So it'll give me minus 2x minus h plus 9 over h, and we're going to do that as the limit of h approaches 0. Notice these two h's cancel, and we are dealing with a polynomial up here. And if we put 0 in for h, that's going to give us negative 2x plus the 9, because the 0 will go here at the h, and that'll cancel that out. And so this will be our limit as h approaches 0. Our answer will be negative 2x plus 9. So notice that the limit dealing with the difference quotient is using a lot of algebra. We have to be careful with our signs. In example 3, we're going to find the limit as x approaches infinity, given that f of x is equal to 2x to the fourth plus 3x. So we're going to look at the limit, and this is not going to be too hard, as x approaches infinity of this function. Well, by looking at the graph and remembering that our end behavior of functions, when dealing with polynomials or end behavior, notice that the exponent is even and that we have a positive in the coefficient of the highest exponent. So that means that we learned back in algebra that this will give us up on both ends. And so as x approaches infinity or heads this direction, we notice that the value is getting higher and higher. Therefore, the limit as x goes to infinity of this function is going to be infinity. We're looking at the limit as x approaches infinity, or as x gets bigger and bigger, of a rational function. Now remember, we're looking at a rational function that's going to have a restriction in the domain. So let's go find the restriction. So we're going to take the bottom, and it can't be equal to 0. We're going to add 3 to both sides. And so that'll give us 2x is equal to 3, and we're going to divide by 2 on both sides. So x cannot be equal to 3 halves. And it doesn't have a common factor in the numerator, so we know at 3 halves, which is somewhere between 1 and 2, we have a vertical asymptote. Notice that the graph looks like this, and notice that as x heads off toward infinity, this thing is getting lower and lower and lower, and it's heading towards 0. So the limit of this would be equal to 0.